Algebra 2, Chapter 1.1, Domain, Range, and Behavior. This is going to be a long video in that it really is from our textbook. And our textbook explains quite thoroughly the concepts of domain, range, and behavior. How you can determine the domain, range, and end behavior of a function. Essential question. What over some key vocabulary. Interval, domain, range, end behavior. Interval. What is an interval? An interval is a part of a number line without any breaks. Finite interval has two endpoints which may or may not be included in the interval. So here we have an example of a number line, and here we have between -5 and 3 an interval with no breaks. But you have this thing right here, open circle is be greater than 5, but less than or equal to 3. So these would be called our end points. And this is one that is not included in the interval, this -5. And this one here is included. So 3 is included, but -5 not included. That is a finite interval. So verbally we'd say greater than -5 to 3. Next, an infinite interval is unbounded at one or both ends. And here we have this arrow pointing to the right, unbounded. So this is an example of an infinite interval. This infinite interval is x is greater than -4, and we can write that as x is greater than -4. Okay. Suppose that an interval consists of all real numbers greater than or equal to 1. You can use the inequality x is greater than or equal to 1 to represent the interval. So what does that look like? Let's go back and see what that looks like. So let's draw a number line. So 1, the critical number here, we write that out. It says greater than or equal to 1. So we draw what says greater than or equal to, we draw a point here, which is represented by that dot, and we go to the right. And that's really what it looks like. And there are different types of notations we're going to look at here in a little bit. Here are the types of notation we'll be using to describe intervals in the domain ranging function. Verbal, number line, inequality, set, and interval notation. So notation is a way of describing something, a type of language, if you will. Okay, and that's what I say here. Notation or notation type of language. Notations are used to describe intervals. All these intervals here. Okay, so now we have a table, and we're going to go ahead and outline everything, what this is now. I've filled in the table here, and this is one place where it might be worthwhile to just stop the video and copy this table down. And what you have, so you can just pause the video. We'll go on after that. All different types of notations here. And all this on the left side here, this is all verbal notation. Okay. Verbal or with language. So really in algebra we try to learn to translate between different notations and different values. So here we have an example of set notation. And what we do is we say, explain this. This little vertical line segment, verbally we'd say x such that And set notation, we don't seem to use it as much, but in case you get, we don't want you to be ambushed on an SAT or something like that, or some other kind of test, and not really have some exposure to this. Interval notation. Okay, what this is, we have a bracket and a parentheses. And what this means, in this case, is you have our endpoints are at -3, and also at 5.5. But we have the bracket, so that's the same as greater than or equal to, and we go to 5.5, well, that's going to be open point or open circle, because that's so number line notation, that's what this looks like. So fluency between the different types of notations, that'll be helpful. Interval notation, greater than or equal to -2, less than infinity. Okay, again, for number line, it's going to look like this. We have -2, we're greater than or equal to, so there we have our point, and we go to the right toward infinity. So that's what the thing looks like graphically. Greater than or equal to -2, less than infinity. Okay, let's go on. Next one. Here we have greater than -infinity, less than 5. So we have at 5, that's going to be a critical number. And less than 5, that's going to be open point or circle. And we're going toward -infinity. So you can just draw an arrow to the left. So that's what that thing looks like in number line notation. Inequality notation, x is greater than or equal to 1. Again, the number line version of this is going to be 1, and greater than or equal to is going to be that open point there to the right. Now we can change this to interval notation. X is greater or equal to 1. Okay, open bracket, 1, comma, and we're going up to less than infinity. That's going to be an interval notation. So number line, interval notation, inequality notation. And there we have, that's interval notation. That's a different interval, of course. What would that look like in inequality notation? Well, that would be x is greater than 1. Not greater than or equal to, because we have this parentheses. So you got to be looking for brackets and parentheses and this greater than or equal to sign, and or just greater than. So we just got to be careful of what we're looking at. Okay, now some exercise. Copy and complete the table. Write the finite interval shown on each number line as inequality using set notation and using interval notation. I'm just going to go through these. We have a finite interval here on a number line. We write this as inequality notation. So that's going to be x. We know that x is going to be greater than -3, but because we have the point that's closed, we know it's going to be greater than or equal to, and x is going to be less than 2, but because that point is a solid point, less than or equal to. So that's what our inequality notation looks like. Now we have set notation, very similar to inequality notation. So we put the bracket first. We put x such that x is, well, we're going to go between the two, so I'm going to go ahead and leave myself some more room, such that x is greater than or equal to -3, but and less than or equal to 2. So very similar to inequality notation. And finally, interval notation, which should be a shorthand of it. What we have is we have greater than or equal to -3. So that's open bracket, -3, comma, 2, and it's less than or equal to. So here we have the closed bracket here. Okay, I invite the viewer here to just sort of work on this one at the right. You have this number line. So you can just pause and see if you can work this one out. Okay, what this is you have arrows going both directions. So you have the entirety of real numbers. So in inequality notation, x is going to be greater than negative infinity, but less than infinity. Okay, so in the set notation, we have x such that x is greater than negative infinity, but less than infinity. And also you have the script R, all real numbers. You may have seen that, the script R, which means all real numbers. You'll run into that sometimes. What is interval notation? Well, we just have open parentheses, negative infinity, comma, infinity. This represents all real numbers. You see how interval notation is a pretty handy notation? There's really less to write, and so it's really more concise than most of the other notations. Let's see. Here we have I think this one is the same one here we had earlier, but on the right we have a different one. So you see the distinction here? Okay. Instead of having less than or greater than or equal to -3, we have greater than. So inequality notation, x in this case is greater than -3, but less than or equal to 2. And in set notation, we have the open bracket here, x such that x is greater than -3, but less than or equal to 2. Okay, and then interval notation, we have greater than -3, comma 2. So that's what that looks like. And let's go on to these two here. You can just pause the video and then just work ahead and see if you got it right. Okay, on the left side, inequality notation, we have x is less than or equal to -2. So x is less than or equal to, I said -2, should be 2. In set notation, x such that x is less than or equal to 2. And finally, in interval notation, we have greater than negative infinity, comma 2, bracket. Now this one on the right, we have x is greater than 2. You know, x is greater than 2. We have, for set notation, x such that x is greater than 2. And the last one, interval notation, we have x is greater than 2. So you put the smallest thing here first, which is 2. And we're going greater than 2 and less than infinity. By the way, with the infinity, either positive or negative infinity, you're never going to have a bracket. It's always going to be parentheses. So you got on tests that'll come up sometimes where you might have a bracket with an infinity. Those are long answers. Reflect. Consider the interval shown on the number line. So we have that interval. Looks like we're going for all real numbers. Represent the interval using interval notation. Well, again, it's one of the ones we looked at earlier. We have greater than negative infinity, comma, less than infinity. That's what that looks like. B, what numbers are in this interval? Well, verbally, we say this all real numbers. And sometimes you'll see all reals, all real numbers. Sometimes you'll see this as this script R. Okay, that's sometimes where you'll see all real numbers. So there are different ways of saying all real numbers. What do the intervals 0, 5, all these different intervals have in common? Well, they have in common endpoints. Okay, endpoints of 0 and 5. Also that these are finite, right? Finite intervals, right? What makes them different? Well, you could say brackets and parentheses are different, greater than or less than or equal. So I'll just simplify. I'll say brackets and parentheses representing greater than or equal to, or less than equal to, greater than, less than. Parentheses, I'll just abbreviate it, parentheses. Next, discussion. The symbol U represents a union of two sets. What do you think that the interval from negative infinity to 0, union U to positive infinity represents? Okay, what this means all real numbers except 0. And so on a number line, what this would look like is this crazy looking thing here. You draw 0, and on the number line itself, you have an open point here, and to the right, you're going toward infinity, and to the left, you're going toward negative infinity. So that's what that crazy thing is. Next, the domain of a function fx is a set of input values x. The range of function is a set of output values f of x, or y. You'll see that as y sometimes. The end behavior of a function describes what happens to the f of x values as the x values either increase without bound, approach positive infinity, or decrease without bound, approach negative infinity. For instance, consider the graph of a linear function shown, and you have this linear function here, f of x equals x plus 1. And we have a statement of end behavior. And this is another thing that you can copy down and could be of help to you. It shows end behavior notation. And end behavior is not how you act just before you're ready to die. Somebody made that joke. All right. Example 1, write the domain and range of the function as an inequality using set notation and using interval notation, also describing the end behavior of the function. So what we have for a domain and inequality notation, well, our domain is going to be all real numbers. So in inequality notation, we would write that down as x is greater than negative infinity, but less than infinity. Okay, this is the parent quadratic function. Set notation, bracket, x such that x is greater than negative infinity. Let me make a little more room here. But less than infinity. So we put a bracket here at the end. And interval notation, we do that as we have done earlier. We have open parentheses, negative infinity, comma, infinity. Okay, range. Now range is going to be output values, inequality notation. So our lower limit is this x-axis. So in inequality notation, our range is going to be y is greater than or equal to 0. That's going to be it. In set notation, very similar to inequality notation. So we have y such that y is greater than or equal to 0. And finally, interval notation, we have a open bracket 0, comma, to less than infinity, rows of parentheses. End behavior. So for end behavior, we're looking back at this statement here. As x approaches positive infinity, f of x does what? So we will say, let me get a little bit finer writing here. Okay, as x approaches positive infinity, what does y do? This arrow means as x approaches positive infinity, y goes up toward infinity also. And instead of y, we're going to say f of x. We use our function notation. F of x approaches positive infinity. Okay, and next, as we're going to go the other direction to the left, as x approaches negative infinity, f of x approaches negative infinity? No, approaches infinity, which is positive infinity. Same thing. So either going to the left or right will give us the same end behavior either way. Next, now we have the domain ranges, inequalities, and set notation, and using interval notation, we have this exponential function. The domain is going to be, we are going through all real numbers. An exponential function has in its domain all real numbers, so that's going to be x is greater than negative infinity, less than infinity. Our set notation, bracket x such that x is greater than negative infinity. Oh, that doesn't look right. I want to be legible here. Greater than negative infinity, less than infinity. And finally, interval notation, open parentheses, negative infinity, comma, infinity. Now for range. Now we have the y value, the lower boundary of the x-axis of 0, but not equal to 0. So x is not going to be greater than or equal to 0, but greater than 0. And so our set notation is going to be bracket x. Well, I got that wrong already, don't I? It should be y. Y is greater than 0. And then we have set notation, y such that y is greater than 0. And finally, our interval notation, we have, do we have a bracket? No, we have parentheses because we have greater than, not equal to. So 0, comma, infinity, and close with parentheses. So there we have it. In behavior. Okay, as x approaches infinity, or I'm going to say positive infinity, f of x approaches also infinity, or positive infinity. Next, as x approaches negative infinity, f of x approaches what? Well, we're not approaching negative infinity here. We're approaching the x-axis, so we're approaching 0. Next, why is the end behavior of a quadratic function from the end behavior of a linear function? Well, you can just think of that, but for a linear function, you're going to go something like this, right? For a quadratic function, you're going to have an opening upward, or in this case, an opening downward parabola. So in this case, your domain for each is the same, but your end behavior is different. You have to, with a quadratic function, in the same direction at the beginning as you start. For the exponential function, f of x equals 2 to the power of x. If the f of x value decreases, and y of x value decreases, why can't you say that f of x approaches negative infinity as x approaches infinity? Well, we see this right here, because we're not going down toward infinity, we're going to the 0. Okay, your turn. Graph the right quadratic function f of x equals negative x squared is shown. Write the domain and range of functions, inequality, set notation, interval notation. I'm not going to spend time going over this one here. I invite you, the viewer, to go ahead and do that. You're going to have something similar to what we did earlier, so you can turn back and look at that. Graphing a linear function on a restricted domain. Okay, I introduced that little script R earlier. Well, here we have it. We see it right here. Many functions such as linear, quadratic, and exponential functions are defined for all real numbers. Okay, and this is how the set of all real numbers, this scripted R, and then the interval notation, which we've seen previously, is this greater than negative infinity, less than positive infinity. Sometimes a function may have a restricted domain. If the rule for a function in its restricted domain are given, you can draw its graph and then identify its range. In restricted domain, what this means is that in the real world, that's where you find restricted domains, and also probably restricted ranges. So here we have example 2. For the given function domain, draw the graph and identify the range using the same notation as the given domain. Well, we can do this a number of ways. One way to do this is we can find, we know this linear function, if we find our input value, we take our input value of -4, f of -4 is going to be 3/4 -4, replacing that x, plus 2, and for that we get a -4 over 4 will cancel, so we get -3 plus 2 equals -1. So where x equals -4, we know that our output value is -1. And we know that it's going to be, we have brackets, so that's going to be equal to, and we can also find f of 4, and that's going to be 3/4 times 4 plus 1. Oh, I said plus 1, let's say plus 2. So 4 and 4 cancel, we get 3 plus 2 equals 5. So we put f of 4 is equal to 5. So that's what that looks like. And so what are we talking about here? We're talking about this interval between these 2 points. And the interval does not go beyond those 2 points. And so these values of -4 and 4 are what restrict this domain and makes the graph the function like we see it right here. We see we have a y-intercept, we have an x-intercept. We can figure out what those are, but this interval takes place on a restricted domain or a finite domain. Okay, next. B, f of x equals -x minus 2 with domain x such that x is greater than -3. Just take a hand at that. I'll work it out. Okay. First thing I'm going to do is, like we did earlier, I'm going to go ahead and substitute in this x is greater than -3, so that -3 is an endpoint. So I'm going to put f of -3 is equal to negative. We put a -3 minus 2. And that's going to be negative -3. That's going to be 3 minus 2 equals 1. So where f equals -3, at -3, we have 1, but greater than that, right? So we put in 1, so that's going to be an open circular point. And we're going toward infinity, so what we have is a slope of -1. So that means we're going to be going down in this direction at a slope of -1. And this is what a slope of -1 looks like. Okay, there we go. So this is what the graph of this function looks like. That's supposed to be an open point right here. Okay? That's what that looks like. Okay, next. In part A, how does the graph change if the domain is f and I don't even have that here. I think it's supposed to look like this instead of that. Well, you just don't have the endpoints looking the same. Part B was the end behavior as x increasing without bound. Why can't you talk about the end behavior as x decreases without bound? Let's say in part B. Yeah, x is not decreasing without bound, right? That's why we can't deal with that. Okay, your turn. In 9 and 10, for given rod, identify the range using the same notation as a given domain. Okay, for this one here, for 9, if we plug in -6, f of -6, that's going to be equal to -1/2 of -6 plus 2, which is going to be -1/2 of -6 is going to be 3 plus 2 is equal to 5. So for x equals -6, there it is, we have 5, and that's less than or equal to, so that's going to be that. Okay, next we have f of 2, so f of 2 is equal to -1/2 times 2 plus 2. And that's going to be equal to -1/2 of 2 is going to be -1 plus 2, so it's going to be equal to 1. So to plug in 2 for x, we get 1, but it's less than, so that's going to be open circled. So we're talking about this interval here like this. That's not too, see if I can get a little more straight looking. That's a little more straight looking. Okay, so that's what it looks like. And so what is our range going to be? Well, our range is going to be y is greater than 1, but less than or equal to 5. So it says same notation. So it says same notation. And so we're going to use our inequality notation. So y is greater than 1, but less than or equal to 5. Okay, so that's number 9. Okay, number 10, we have this business here. Fx equals 3 halves x minus 1 with domain from negative infinity to 3. So you can plug in 3, f of 3, to get an endpoint. It's going to be 3 halves times 3 minus 1. And so for that, we get 3 times 3 is 9. So we get 9 halves minus 1. And 1 is the same as 2 over 2. So we can just rewrite that minus 1 as 2 over 2. So we get 7 halves. So we plug in 3 for x. I'm going to go ahead and do this in red for color coding purposes. We plug in 3 for x, we get 7 halves. Well, 7 halves is like 3.5. So right here, that's going to be greater than or equal to, and the slope is 3 halves x, well, 3 halves x minus 1. So that's going to be our y-intercept of negative 1. So the thing is going to go like this. And so we're extending negatively down toward negative infinity. And then the thing will, as x increases, go up and just stop here. Okay. So that's where the graph of the function ends. So I hope you can see that. Modeling with linear function. Recall that when a real-world function involves a constant rate of change, a linear function is a reasonable model for a situation. The situation may require restricting the function's domain. And here we have Joyce jogging 1 mile every 10 minutes for a total of 40 minutes using inequalities for domain and range that models the situation. And so Joyce's jogging rate is 0.1 miles per minute. How do we find that? Is we put 1 mile divided by 10 minutes. And that's equal to 0.1 miles per minute. Next, for jogging distance d in miles any time, t is modeled by d of t equals 0.1 t. And because that's going to be our rate of change, right? So that's going to be our function. Next, since she jogs for 40 minutes, the domain is restricted to this interval here between greater than or equal to 0, but less than or equal to 40 minutes. And here we have the domain. Let's graph this function here. So between 0 and 40, and she's going up at 0.10 minutes per mile. So how far does she go? 1 mile for every 10 minutes. Well, that's going to get her up to 4 miles total. So in 40 minutes, she's going to cover 4 miles, and the thing's going to look like this. So that's what it'll look like. Again, restricted domain. Okay, and then what is the range going to be? Well, the range is going to be, I have it right here. The range is going to be from 0 to 4 miles. So that's where we get this, the range is D is greater than or equal to 0, but less than or equal to 4. So that's where that comes from. Next, a candle 6 inches high burns at a rate of 1 inch for every 2 hours for 5 hours. So we have 1 inch per 2 hours. So that'd be 1/2 inch per hour. Okay. So, yeah, or negative 0.5 inches per hour. The candle's height at any time is modeled by the equation 6. If we start out at 6, that's like our y-intercept. And since the candle burns for 5 hours, the domain is restricted to the interval from 0 to 5. And here we have it. And what does that look like? Well, we're starting right here at 6. We're going down 1/2 inch per hour. So we're going down to, for 5 hours, to 5. And 1/2 inch per hour. Now, if we plug in 5, we can see this. Okay, h of 5 for 5 hours is going to be 6 minus 0.5 times 5. And that's going to be 6 minus 2.5, so it's going to be 3.5. So we're going to 3.5 inches in height. So this is what the candle is going to look like, or the graph of that. Okay, restricted domain. And the range, what's the range going to be? Okay, between 3.5 and 6. So range okay, we have y, or height, right? Height is going to be greater than or equal to 3.5, but less than or equal to 6 inches. That's going to be our range. Yeah, there we go. Okay. Next, suppose Joyce jogs for only 30 minutes. So then it asks you to change. I'm not going to do this. You can go back and look at that. I'll just let you do that. Modeling with linear function. While standing in a moving runway airport, you're carried forward 25 feet for every 15 seconds for a minute. Okay. So just work this out. Use a set notation. I'm not going to do this at this point. You might be able to do this in class. Elaborate. If A and B are real numbers such that A is less than B, use interval notation to write 4 different intervals involving A and B as endpoints. And so we can just quickly kind of see what they are here. If you have A to B, we have one situation here. We're going to have 4 different situations. I'm going to put them in the same place. Okay, A and B. Third case, A and B. And the fourth case, A and B. Okay, you can have, I'm going to use red here. You can have A and B are both closed circles. You can have them be both open like this, greater than A, less than B. You can have A be open and B be finite like this. Or you can have A be a point included and B is less than or equal to. These are 4 different possibilities we have with 4 different possibilities with A and B as endpoints. Okay, what numbers? You can write this out in interval notation, what numbers they include. You could say, okay, this one here is going to be A, comma B with brackets on both sides. This one here is going to be A, comma B, like this. This next one here is going to be greater than A, but less than or equal to B. And this last one is going to be greater than or equal to A and less than B. So that's what they look like in interval notation. What impact does restricting domain of linear function have on the graph of the function? We kind of seen that with the Joyce jogging and the candle and the other examples. So that should be kind of self-explanatory. Essential question check-in. How does the slope determine the end behavior of linear function with unrestricted domain? Well, the end behavior doesn't change what the slope is, because here if we have a graph and we have a slope of, we have a very steep slope like this, our end behavior is going to be the same as if we have one with a very shallow slope like this. Because the thing is still going to go, well, I'll try to draw it more straight than that. It looks better. Our end behavior in each instance is going to be the same. It's just not going to get there as fast. So really that's it. That's a long video, but the investment, I thought it was worth it because it really covers a lot of key concepts for which a solid understanding is needed for success this year in this course. Good luck. Thanks for viewing.